Suppose we set up a Cartesian coordinate system as shown in the screen, where x is pointing to the right in the screen, y is pointing into the screen and z is pointing upward. Now suppose we have a thin film of yttrium iron garnet. The film extends to infinity in the positive and negative x and y directions. This thin film is 20 nanometers thick. Then, we place a cobalt iron boron stripe on top of the yttrium iron garnet film. This stripe extends to infinity in the positive and negative y directions. The vertical separation between the film and the stripe is 12.5 nanometers. The stripe is 50 nanometers wide and 2.5 nanometers thick. On the other hand, we apply a global bias magnetic field in the positive y direction. Magnetic moments in the yttrium iron garnet film is also aligned in the same positive y direction. While at the same time, magnetic moment in the cobalt iron boron stripe is pointing towards negative y direction. This can be achieved by proper bias magnetic field cycling history. Suppose now we send in spin waves in the yttrium iron garnet film from the left. Because of magnetic dipolar coupling, the spin waves in the yttrium iron garnet film will excite a resonance mode in the cobalt iron boron stripe. In this case, the cobalt iron boron stripe is called a chiral magnonic resonator. Incident spin wave energy in the yttrium iron garnet film will be dissipated in the chiral magnonic resonator, and this phenomenon is called resonant absorption. Because the majority of incident spin wave energy from the left is being absorbed by the chiral magnonic resonator, the amplitude of spin wave transmitted to the right side of the yttrium iron garnet film has been reduced substantially when comparing to the spin wave amplitude on the left side of the film. Suppose now we place a layer of magnesium oxide on the top of the cobalt iron boron stripe. Then we place a bottom and top electrode sandwiching the cobalt iron boron and magnesium oxide structure. We then apply a voltage between the top and the bottom electrode. By a phenomenon called voltage-controlled magnetic anisotropy, we would then be able to tune the cobalt iron boron stripe out of resonance with respect to the spin waves in the yttrium iron garnet. The cobalt iron boron stripe cannot resonant absorb spin wave energy in the yttrium iron garnet as efficient as before, and therefore amplitude of transmitted spin wave to the right side of the film increased. Now if we switch off the voltage, then the cobalt iron boron stripe will be back into resonance with the spin wave, and the spin wave amplitude on the right side of the film is attenuated. And if we turn the voltage back on, again the cobalt iron boron stripe will be off resonance with respect to the spin wave in the yttrium iron garnet film. Therefore transmitted spin wave amplitude to the right side of the film is increased again. Therefore, by switching off and on the voltage applied to the electrodes, we would be able to control the transmitted spin wave amplitude in the yttrium iron garnet film underneath the cobalt iron boron stripe. Effectively, we have created a spin wave valve that is controlled by an electrical voltage. The cobalt iron boron stripe in this case is called an electric chiral magnonic resonator. However, there also exists another type of electric chiral magnonic resonator. Suppose instead of applying a voltage across the cobalt iron boron stripe thickness, we apply the voltage laterally across the bottom electrode as shown. An electric current will flow in the bottom electrode towards the negative x direction. If the bottom electrode is made of heavy metal such as platinum, a phenomenon called spin Hall effect will occur, which scatters spin polarized electrons in the platinum upward into the cobalt iron boron stripe. These spin polarized electrons will exert a spin orbit torque to the magnetic moment of the cobalt iron boron stripe. This would lead to negative damping of magnetic resonance inside the stripe. Now if we just like before send in an incident spin wave from the left in the yttrium iron garnet film, after passing through the underneath of the cobalt iron boron stripe, the spin wave will be amplified instead of being attenuated. This manifests as a larger outgoing spin wave's amplitude away from the cobalt iron boron stripe to the right than those which are coming in from the left. This phenomenon is called spin wave resonant amplification. The cobalt iron boron stripe in this case is called a spin-orbit torque-driven electric chiral Magnonic resonator. Because of its low damping properties, yttrium iron garnet has been the preferred material for Magnonic's application. However, spin wave amplification in yttrium iron garnet has been a long-standing problem in the Magnonic's research community. At this moment, the electric chiral Magnonic resonator proposed here in this video is one of the few viable solutions for spin wave amplification in yttrium iron garnet. If you want to know more about electric chiral Magnonic resonators, please follow the references provided by the hyperlink below in the video descriptions. Also, please press the like button and subscribe to our channel. Thank you very much.